I want to solve these two logarithmic equations, and I want to solve them both using the same method. Logarithms are one-to-one functions. So if I have the log base b of m equals the log base b of n, I can solve this just by saying, well, m has to equal n. I can set the insides equal to each other. Please do not ever say you're canceling out the logarithms, because that's not what we're doing. You can't divide both sides by a logarithm without something on the inside. They're functions. So we're not crossing those out. We're saying, hey, if these two logs are equal, then their insides, they have to be equal. We're setting m equal to n. So when I look at this problem, I see two logs on this side and one on this side. I want it to look like this, so I'm going to condense these two logarithms. All right, so I need to multiply these. I'm going to go on and distribute 3x plus 9. Now I can set the insides equal to each other. I'm setting the arguments equal to each other. 2x minus 1 is equal to 3x plus 9. Take 2x away from both sides, and I will get x equals, and if I go on and take 9 away, I get minus 10. So it looks a lot like x is going to be equal to minus 10, and this is where, like, if we just stopped, we would have made a really bad mistake. Because if I go to try to check my answer and plug that in, I'll get the logarithm of, and then I say, well, minus 10 times 2 is minus 20, minus 21. And right there, without even looking at the other side, I say, well, I can't do that. I can't take a logarithm of something less than 0. Because the inside of this logarithm is less than 0 when I plug in x, this can't be a solution. It's also not in the domain of this side either, right? Minus 10 plus 3 would be minus 7, right? It's not quite as large, far away from 0 as minus 10, but it's still less than 0. So that can't actually be a solution. So this one has no solutions. And that's my final answer, because when I went to check my answer, I got something less than 0 on the inside of at least one of those logarithms. All right, so let's see if we can do this one. Let's see if we actually get a solution this time. So now I need to condense both sides of the logarithm. I need to remember that subtraction means I'd be dividing. And now again, I have the natural log of m equals the natural log of something else. Natural logs are one-to-one. All logarithms are one-to-one, so I can set the insides equal to each other. So x minus 2 over x plus 3 equals x minus 1 x minus 1 over x plus 7. All right, so this is the equation I have to solve. I suggest multiplying both sides by the least common denominator. You might know it as cross multiplication. But any way in which you do it, the next thing I have is x minus 2 times x plus 7 is equal to x minus 1 times x plus 3. Let's distribute on both sides and see what we get. All right, after we multiply this side out, we get x squared plus 5x minus 14. And on this side, we get x squared, and let's see, plus 3x minus x is plus 2x minus 3. Well, right now, this looks like a quadratic equation, so I need to get everything on one side. But when I subtract x squared from both sides, I find out those cancel. I can then take a 2x away from both sides. And so I'd have 3x minus 14. 3x minus 14 is equal to minus 3. I add 14 to both sides. 3x is equal to 11. And so x is equal to 11 over 3. Well, 11 thirds minus 2 is positive. 11 thirds plus 3 is positive. 11 thirds minus 1 is positive. It seems to work in all those logarithms, and what we actually should do now is get out our graphing calculators and actually type in exactly this and write down what we get, and then compare it to what we get when we plug 11 thirds into that. But I'm going to let you do that.